Okay, good morning, everyone, and welcome to the Shannon Lecture. This lecture is presented by the winner of the Shannon Award, which is our society's highest honor, given for consistent and profound contributions to the field of information theory. Shannon, as we all know, was a mathematician and an engineer whose theories laid the foundation of the information age we live in today. His ideas have inspired and shaped our community for over 6 decades, and they continue to do so today. This year's lecture will be given by the 2014 Shannon Award winner, János Körner, who has made fundamental contributions to the core of information theory, as well as its applications to diverse topics in computer science, combinatorics, and mathematics. For the sake of time, I will only mention a few of János' best-known results and try to show how they were truly an integral part of his life and prolific research career. János received his diploma in mathematics at Loránd Eötvös University in Budapest in 1970. This is the same university that graduated Paul Erdős, Laszlo Lovas, Imre Cizar, Peter Gash, and Kathleen Marton, among other world-renowned mathematicians. After graduating from Eötvös University, János joined the Mathematical Institute of the Hungarian Academy of Sciences, where Imre Cizar and others had been working on several aspects of information theory. This helped spark János's lifelong interest in the combination of mathematics and information theory. It didn't take long for János to come up with his first information-theoretic discovery. In 1971, just a year after he graduated, János published his first paper on graph entropy, a functional that relates not only graphs and entropy, as the name suggests, but also chromatic numbers, graph products, and subadditivity. Graph entropy has since become an important concept and a tool for many applications in information theory, combinatorics, and computer science, including to perfect graphs, communication complexity, and function computation. 3 years later, in 1974, János visited Rudi Alzweda in Columbus, Ohio. Rudi was working on the nascent field of multi-user information theory, and János became very interested in the subject and subsequently made many important contributions to it, including establishing the capacity regions of the broadcast channel with degraded message sets and with confidential messages, introducing the classes of less noisy and more capable broadcast channels, establishing the rate region of source coding with side information, and showing in his now very famous paper with Kathy Marton, coding for the mod2 sum of 2 binary sources, that structured codes can outperform random codes in multi-user settings. János' work on the broadcast channels has greatly influenced my early work when I was starting out as a graduate student. I still fondly remember my first meeting with János at the 1977 ISIT in Ithaca, how generous and supportive he was of my results. At the end of his 1974 visit to Rudi Alzweda, János was so excited about multi-user information theory that he drove very fast from Ohio to Bell Labs in New Jersey to discuss the results with Aaron Weiner. He got ticketed twice for speeding. However, he apparently found the law enforcement loophole and supposedly has not paid the tickets to this day. I'd like to say that we are accepting the ticket amounts as a donation to the Information Theory Society. János subsequently returned to Hungary and spent the next few years with Imre Cizar writing their seminal book, Information Theory, Coding Theorems for Discrete Memory Systems, which was published in 1979. Much more than an introduction or a survey of information theory at the time, the book contained many new and innovative results, which many of us have greatly benefited from. Perhaps one of its better-known contributions was the first comprehensive treatment of the method of types, which has become the technique of choice for many information theory proofs. Both János and Emre are real perfectionists with very strong opinions. So I understand that the book was rewritten at least 3 times before reaching its final form. And if you think this is tough, imagine that this was done before LaTeX and other typesetting programs existed in Hungary, and maybe even in the US, actually. So everything had to be done manually. Sometime after that, János visited Giuseppe Longo in Italy. They had a long-standing technical collaboration, and the story goes that shortly after his first visit started, János started answering Longo only in Italian. This reflects not only János's polyglot nature, and he speaks 5 languages, and he told me that the languages that he really knows he doesn't speak, so there are more than 5. But also of the beginning of János's love affair with the Italian language and culture, which resulted in him moving to Italy, where in 1993 he became a professor of computer science at Sapienza University in Rome. While in Italy, János continued his work on combinatorics and extremal mathematics that was both motivated by, used techniques from, and was useful for information theory. He has made many important contributions in this area. Perhaps one of the better known was the introduction, together with Luisa Gargano and Hugo Vaccaro, of the Sperner capacity, which generalizes Shannon's graph capacity to directed graphs. Sperner capacity has subsequently been used to derive new results on coding, zero-error communication, and János and Luisa and Hugo used it to solve a 2-decade-old open problem by Régnier on qualitative independence, thereby completing a full circle of János's interests and interactions. For these outstanding contributions and many others to information theory and mathematics, János was elected as an external member of the Hungarian Academy of Sciences. Please join me in welcoming the 2014 Shannon Award winner, János Körner. Before we begin, I just have one request. Please put your phones on silence. The penalty for hearing your phone will be extremely severe.
Okay, so is it okay? Yeah, so I want to thank Abbas for his generous words, and I feel very honored and moved that I can stand here and talk to you whatever I am interested in, and that I, for myself, consider information theory, and I hope you also will. So, so I would like to talk as the title is somewhat mysterious, and I hope that I will clear this up. I won't explain it right away, so it should come through. I have so little to talk about left by Abbas, so I feel a little bit embarrassed, but I will try. Okay, so now this is the title, and so I will begin by showing you some pictures that illustrate what Abbas said. You see, all over Eastern Europe, and especially in Hungary, there was this particularity that information theory was considered an integral part of mathematics, and even pure mathematics. And this is a school created by Alfred Rényi, whom you can see to the left here. And well, actually, while Rényi had never been interested in coding problems or IEEE type information theory, as I might say, as I like. He was nonetheless the founder of an entire group on information theory, and this group was then directed by Imre Csiszár towards IEEE and the coding problems. since Cesar insisted that information measures that were at the center of Rény's interests should be justified by, should have an operational meaning, and therefore should be justified operationally. And this had a very important impact on me right from the outset. To the right, you can see my favorite building and part of Budapest, which is the Mathematical Institute. And I should say that I feel no nostalgia for Hungary except for this institute that I truly love. Okay. So, and here comes Imre Cesar, whom you all know, and this is a picture of him, very typical while he is lecturing. Mm-hmm. And so I also would like to show you the picture of Péter Gács. So you see, I wrote my first papers all by myself, but I have always preferred to work with someone else, mostly with just one other person. And this is why I wrote my third paper with Péter Gács. So we were very distant, and then we somehow got to the same problem. We realized that we both had kind of a solution, and then we started to write a paper together. And this is how, from quasi-enemies, because of the Hungarian situation I don't want to talk to you about right now, I mean, the Hungarian situation at the time. So we became friends, and I learned from him how to write a real paper in real mathematics, and I also learned many other things from him. And he's a dear friend that I am in touch with even today. So we went to the same class, maybe I have not told that. And so therefore, like I said, during the rest of my career, I have always enjoyed collaboration, and my most intense collaborations were with these three people. So you can have the picture of all of them, but actually there is a live picture next to you of Gábor Simonyis. So, okay, and don't be afraid, I won't talk about my life. So. I just want to mention three other people because, you know, as you might know, Hungary in the early 70s, when I started my career, was a country of the Eastern Bloc, so Soviet rule, and really shut away from the rest of the world, the so-called Western world. And also, we were mathematicians, and there was IEEE, and they were engineers, and even worse than that, they were American engineers. But these people were, I mean, these three people were extremely welcoming, and right from the outset. So in '73, we went, I mean, us, what was called the Hungarian delegation, even the word gives you the taste of communism. So this Hungarian delegation went to Tallinn for this all-Soviet information theory conference, and David Slepian was there, and so I knew about the Slepian-Wolf theorem, but I knew nothing about Slepian. And Slepian, right when he met me, told someone else, I don't remember who that was, oh, here is an author of the Hungarian paper. Because it turns out that they were, thinking about the same problem that Péter Gács and I solved. And I still remember how he opened his gold pen, or at least so I remember that his pen was gold or golden. And then he explained me something by writing on a sheet of paper. So I truly cherish the memory of Dave, who was a wonderful person in so many ways. And also, he was he had close ties to Hawaii. Like, in that part of his life, he would spend every second year at the University of Hawaii. And I certainly didn't know at the time what Hawaii means. Now I know that, that he was right even on coming here so often. And well, I won't talk in detail about Aaron Weiner and Jacob Ziff, but those people are very, very important to me in my mathematical life. Okay. So now let me talk a little bit about the modulo 2 sum source network. So this is something that I dealt with in my collaboration with Cotty Martin. And actually, it was somehow the end of my successful part of research life in multi-user information theory. Because this problem is really peculiar and hard. So, I mean, here you have the usual setup of what was considered and what is still considered in multi-user source coding. So you have two correlated sources. So this is the simplest case. So the sources, the joint sources are IID. But the two parts, the X part and the Y part, at every given time instant I, are correlated, have an arbitrary correlation. And so this is something that you consider in general, but we just consider here the binary case, meaning that all the random variables are individually binary. So they take the value 0 and 1. And they are correlated, but they are encoded separately. So one encoder only sees the X source, and the other one only sees the Y source. And they all produce a code of what they see in the first n-time instance, so which is just any function of the source they actually see. And these coded versions of the sources, whatever they are then made available to a common decoder. And in general, the decoder has to decode on some function of the two sources. Even this is a special case of a more general problem that at the time was called the two-hat-one problem. I won't explain. But here in this case, the sources are binary. And so the Z stream that the decoder is supposed to reproduce with a small probability of error is just the modulo 2 sum of the X component and the Y component, which means that what the decoder should be able to determine is where exactly in which coordinates the two component sources differ. Okay? So then you define as usual for an asymptotic evaluation, you just define as usual the exponent of the coding functions and you evaluate them asymptotically. So, say if the X function has an exponent of the cardinality of the number of values, that converges to R sub X, and the same for the Y component is R sub Y, and at the same time, the probability of error is something that goes to 0, then you would say that R sub X, R sub Y is an achievable rate pair, and the general goal is to determine all the possible pairs, achievable rate pairs. And we found this little result with Cotty Martin that we considered at the time not even worth put in writing, but I won't tell you the story of why we finally did. But at today's standards, such a thing would need no explanation because you are so much under pressure to publish because then your age index and all the other indices might have problems, So we proved this result that says that the achievable rate region is very simple. It's just a rectangular region that has this corner point, both of the coordinates of which are the entropy of the Z source, which is, so Z is just a random variable that has the same distribution as all the Z's. Okay? So let me just talk about the proof of this. Now, the so-called converse, that is that nothing outside this region is an achievable rate pair is perfectly obvious, but only because we have this special joint distribution. So for this special joint distribution, the sum is independent of both of the components. So the conditional entropy of z given y or given z x, it's the same thing, is just equal to the unconditional entropy. So therefore, the converse is obvious. Okay? Now, the direct result, and this is the intriguing part of it, is that, we proved it, that by applying the very same linear function. So f is just bluntly a linear function of the input, and so is g, but actually f and g are the very same function. So therefore, if the decoder sums up modulo 2, the 2, then by linearity, this is just this function applied to the sum. And so if this function is an optimal linear code for the sum sequence, then you can get back the sum sequence from this code. Now, so this is a nice, curious little result. But then, with time passing, this became a stumbling block. What is so horrible about this result is that you don't see at all, at least I still don't see, how you could generalize it for arbitrary joint distributions. Say everything is binary as before, but the joint distribution is no more symmetric. At the time we considered, rightly so, that if you can solve a source coding problem just for one type of joint distribution, then you have done practically nothing. Because a solution means that you have the solution for every possible joint distribution. So this is a very, why is this a stumbling block? Because, this code is so peculiar. So you have the very same structure for the code of both component sources. And it's just impossible, I think, to see any way of generalizing this. So what is the hope? Well, the hope is that maybe the way we did it is just too peculiar, but you could do it in a more standard way, which then could be generalized. So, but in alternative, could you prove that there is no other way, actually, to do it than the one we used? And I think that this might be true, but there are no such proofs in general, and I wouldn't know how to do such a proof. So this is a stumbling block, and I got more and more depressed by the fact that I got convinced that, so you watch the black color. So I was really more and more depressed about this, that this is just the tip of an iceberg of difficulties in multi-user problems. And I suspect that there is this kind of a difficulty also for the broadcast channel. And so the difficulty here being that you would need structure, not just throwing around stuff randomly and then declare that that is a code. So, so the conclusion at the end of my writing the book with Imre, my conclusion, because we did not necessarily came to the same conclusion. We were discussing practically every sentence while doing the book, so it's a compromise book. And so I thought that what I should, So I thought that what I should do is try to look for structure, but I really wouldn't know where and why and how. And then, as it happens in life, by chance and by luck, actually, I came across a little puzzle that, and I came across this puzzle because I was at Bell Labs at the time, and so there came Mike Friedman, who at the time was at Rutgers University, and presented a very nice result of his with János Körner. And actually, I didn't understand a word of this talk, but then later I met János Körner in Budapest and asked him, so what was this curious thing about that he used entropies in? And so this is this is a general problem, but the part of it I like to isolate is something that I would call a little puzzle. And we call this little puzzle triference. And you see, I will mention later, this is actually a special case, the simplest non-trivial, and in fact unsolved special case of some well-known problems, and one well-known in standard information theory. Actually, it goes back to Peter Elias. And the other one is in theoretical computer science. But I think that what you should do is to look at such simple problems as such, in their naked beauty, if I may say. Also, well, for one reason, because it's better this way. It's nicer. It's more aesthetically appealing. But the more important reason is that if you bury such a problem under heavy terminology from your preferred field, then nobody outside your preferred field would care for this problem. And I think this is such a basic problem that it should be really interest mathematicians at large, so that maybe someone might come up with the killing idea that would actually solve this problem that is still unsolved. But, I guess this name, triference, that we gave the problem explains why this is so fundamental in my view. Because you see, difference and distinguishing are basically linked, as the word says, to a binary relation. So it's something binary. Two things are either equal or different. But so how would you generalize this for the case of a ternary relation? So for this, you should have at least a ternary alphabet. So say you do have, just to make things as simple as possible, without getting trivial, so you have a ternary alphabet. And then you consider three sequences out of your ternary alphabet. So say it's 0, 1, 2. And you would say that three sequences are different if they actually differ at once in the same coordinate. So you have one coordinate at least a coordinate y, I, where these three strings have the three different values. We don't know in which order, but these values should be different. So this is what we like to call triference by now. And now, as humble and simple and basic this problem is, it's still unsolved. So the lower bound is sort of interesting. I would say it's very interesting because, you see, in such problems, you somehow feel that this is some distinction and such things you can create by just throwing things randomly on the table. So you just use a random choice. And so there is no reason, there seems to be no reason to use a random choice other than plain random choice. Because, everything here is symmetric in the symbols that you have, and the condition is symmetrical. So there seems to be no reason to do something more sophisticated. So it seems that you wouldn't need more structure to do something about this problem. But actually what we proved was that, well, in the end we do use random choice because we have nothing else. We have nothing more sophisticated. But the random choice that we use to get the best lower bound on this problem, which is what you can see on this slide, is a tricky type of random choice. So consider the tetrachord. I won't explain what it is. Usually what is called the tetrachord is a linear code, but it's not important that it be a linear code. It's just length 4 code on a ternary alphabet, and which has the property that the distance between the Hamming distance between any two of these small strings is uniformly 3. And as a consequence, no, I should say 3. And as a consequence of this is very trivial to see, these 9 strings are different, and you wouldn't be able to have more. This is optimal. So for length 4, it's trivial that this is optimal. However, you cannot get away with these small constructions for the general case. As the lengths of the strings get longer. Why is that? Well, that's simply because the Cartesian product of a good, the Cartesian powers of a good small construction are not necessarily good constructions. Well, are not good constructions in general. So plain random choice is not optimal. Cartesian powers won't give you anything. So this is really a truly difficult problem. So, but now we have this nice strings that are different, and what we can do, since we have no other more sophisticated tool in general, so we can consider these mini-strings as simply the symbols of an alphabet of size 9. Okay? And now for this alphabet, you do plain random choice. Clear that this won't give you the solution, but this gives you something far better than plain random choice. And this is what we did. So in a way, I claim that here, structure comes in. And well, would you think that this is an information theory problem? I think that it has an information theory flavor in the sense that it should appeal to information theorists because it is like problems in the Shannon theory. So, I mean, intuition says this, but actually it is a problem from Shannon theory. So what kind of Shannon theory is this? Well, you see, this is, so Elias, as usual, in one of his classical chefs-d'oeuvres of a footnote to a paper of Shannon, noticed that, well, if you if you consider zero error, but for a list code, and even if you consider list size 2, so, for instance, in the case of this channel, so this is a 3 by 3 matrix, which is the matrix of a DMC. And so these are the probabilities. What matters is that on the diagonal you have zeros, and else it doesn't matter what you have. Say you have uniformly 1/2, and then, so the zero error capacity is 0, but if you allow a list code of size 2, then you can, with positive rate, get 1 bit close to having all the message. Okay? And, well, because the receiver, the decoder, comes up with a list of 2, which means that if the code is good, that one of these 2 is the true code word sent. Okay? And it is perfectly trivial since, the capacity for the channel cannot be larger than the Shannon capacity. I mean, not the zero error Shannon capacity, but the Shannon capacity. So you have this upper bound, which is in Elias's remark. So this is perfectly obvious. However, well, to tell the truth, Elias was not interested in list codes of fixed list size. So he was evaluating the list size asymptotically. So it had to be sub-exponential, but it doesn't matter. Okay? But the point is, and this is a point I want to make in favor of considering mathematical problems in the Shannon theory in their naked beauty, if they are beautiful, and if you can do this operation, because then it won't happen what happened in this case, that the problem was rediscovered with worst bounds, and with bounds that were worse, somewhere else in theoretical computer science. And this one was rediscovered by Fredman, Conlosh. Oh, I shouldn't touch this. By Fredman, Conlosh, and Semerady in '84. And this is how I learned about the problem. But later on, I will show that since what I would like to talk about is how, concepts of capacity, when suitably generalized, can cover an awful lot of mathematics in extremal combinatorics and in theoretical computer science, which at its best is nothing but extremal combinatorics, at least in my patriotic view. So I will show that this problem can be considered, rephrased as the capacity problem for a hypergraph, But for the simplest hypergraph, that is not a classical graph. I mean, a classical graph is a hypergraph, but so where the hypergraph is no more a classical graph. Okay? So in a classical graph, you have so-called hyperedges that are normally called edges, and they have just two vertices. In a hypergraph, the edges, the hyperedges, can have more vertices than two. But now, if you have a hypergraph in which the hyperedges have three vertices, that is a uniform hypergraph. All the hyperedges have cardinality 3, but actually there is only one of them. So that's the simplest hypergraph you can imagine. And the hypergraph capacity, which is just a formal generalization of Shannon's graph capacity, so the hypergraph capacity of this hypergraph is exactly the same value that T sub 3 that I introduced before. So it very naturally fits into the capacity framework. Okay, but more generally, what Fredman and Komlosh considered was BK perfect hashing. So just looked at it somewhat differently. So you have from the opposite direction. So you have a set, M, and now you want to separate the K subsets of this set M by functions that are B-ary. So B is at least K. So you have these functions defined on M that have exactly B different values. So from the same set, say 1, 2, so forth, B. And so you would say that such a family, and now you want to figure out how small this family can be. So you would say that such a family of B-ary functions is a K-separating family if for every K set, every K element subset of M, I don't dare to point because then it jumps, the slide jumps. So I'm sorry about that. So then for every K set, there is at least one of these functions that is injective on that particular set. So how many, one function would separate only so many, and so you would need more functions, but what is the smallest value of these functions? So that's what it's written here. Now, so you can see you have, this is an example where K is 4, so A is a set of 4 elements, and B is 6, and you have this partition, and actually every element of A, so I pretend that these black dots are the 4 elements of A, they fall into different classes of the partition, okay? And so now the point is that, what you would like to have is, so it's very easy to know that what the number of the K sets is that a single partition can separate. So the optimal value you get, of course, if the partition is a uniform partition, so the function takes all its values on a set of the same cardinality. But the point is, so now you would use a volume bound. Well, if one function can separate so much, then I know how many sets I have to separate, and I just divide the number of these sets by the number of sets that one function can separate, and this gives me a lower bound. But this lower bound won't, will remain constant even though the cardinality of M goes to infinity. So it's a very, very poor, this is called the so-called volume bound. It's a very poor lower bound. So the difficulty, why is that? Well, simply because if you have two such partitions, so there are many K sets that are separated by both of them. And as you use more functions, this gets worse and worse. So these contributions of the individual functions overlap. And you should have some measure to evaluate the individual contribution to the complete separation of the individual functions. So this should be some invariant. Now, that's just a general case, a special case of what I would consider a graph covering problem. So this is just a view that you can apply to many problems. And the view is the following. So you have a graph G, and then you want to cover the graph G in the sense of covering the edge set of the graph G by the union of the edge sets of graph G sub I of some particular prescribed type. The type comes from the problem, so from the nature of the problem. And how many covering graphs of this prescribed type you would need to cover all the edges of G. So this is the general thing. And so this is a framework you can consider perfect hashing in. Okay? So this is the question, how many G sub i's of some prescribed type you would need. Now, if you have any subadditive graph functional psi, which means, so here you have what it means, the last green line, that's subadditivity. That would give you a trivial lower bound on how many graphs you need. Now, it turns out that one graph functional that you can use here is graph entropy that you see defined. Now, the point is that in graph entropy you have a free parameter that you can tune, optimally to your problem. So it actually gives you, even though the class of graphs you use to cover might be fixed, I mean, it's given by the problem, P is a parameter that you can play around with freely. Okay? And so this gives the best non-existence bound for perfect hashing for a whole range of the pair of parameters bk. And this is something that I did with Scotty Martin in '88, and it actually improves on what I did 2 years before all by myself. So you see that with a little help from my friends, I could always do better. And actually, I will not enter the details because I just want to give you a taste of how you can use entropy type measures in extremal combinatorics. Okay? So I should say that, just to explain a little bit more, the flavor of graph entropy, that this is sort of a random overlapping coloring in the sense of covering the vertices of a graph by independent sets. So you just create a correlation between the random covering independent sets and the vertices. And you measure this correlation by mutual information. And you want to have as little correlation as possible. Like if you could cover everything by just one independent set, meaning you have no edges, then actually the covering would be independent of the variable on the vertices. So if you only have smaller independent sets and you need many, so what is the minimum correlation that you need for that? So this is profoundly information theoretic because we are measuring independence by mutual information. Okay. Now, this has, much later. So I introduced graph entropy in '71. I did this in the late '80s. By chance, I came back to this. So in the late '80s. And then, so I have talked about the joy of collaborating with Kati Marton, with Imre Csiszár, and with Gábor Simony. But then the four of us, together with László Lovász, we actually proved that the equality in the subadditivity of graph entropy characterizes perfect graphs, which, by the way, is a notion created by Claude Berge, inspired by Shannon's zero-error capacity problem. So since in general, the entropy of the complete graph is just the entropy of the underlying distribution, but the complete graph is the union of a graph, of an arbitrary graph and its complement. So therefore, you would always have that the sum of the entropy of the graph plus the entropy of its complement is at least the entropy of the underlying probability distribution. But if the two sides are equal for any distribution on the vertices, then this characterizes perfect graphs. Okay? So this we proved with Lovász. Okay. And this then, the fact that this characterizes perfect graphs, and that perfect graphs, especially the part that for perfect graphs, there is this full additivity was used, was the basis for pairwise sorting, for sorting algorithms by pairwise comparison. This is something that was done, I will come to this, in a series of papers by important people in theoretical computer science. So this is not our work. So I won't explain this in detail because I want to get to the end. So here are these people who did this. So the first paper on this that introduced this algorithm that was later refined were Jeff Kahn, whom you see on the left, and Jong Han Kim, whom you see at the right. Okay, and then there were later papers. This was applied for quantum computation, sorting, quantum algorithm for sorting by Andy Yao. And then there was this group of people in Belgium together with Jan Munro from Canada who refined this algorithm. And this is apparently a very good algorithm because in these algorithms you have to compute which new pair you should compare so that you could then get more information about the unknown total ordering that you would like to get. So you can, at each step, you only need polynomially many steps to determine this new pair, a new pair that you should compare. And the measure of the progress of this algorithm is again measured by graph entropy. And what is important is that these graphs that describe what you already have are so-called comparability graphs, and those are perfect graphs. So really the full strength of this is exploited in this. But now I would like to talk about, as much as I can, about graph capacities, because the most interesting, at least to me, part of all this, what I've done since I have left, not information theory, but say I have temporarily left multi-user information theory for these things, was to generalize Shannon's original concept of zero-error capacity in several different ways, and combining these generalizations. And then that could be used to solve existing problems. So it's not just problems we made up, but problems that were there before, as Abbas mentioned. Okay, so actually the graph capacity problem of Shannon's was made famous in graph theory by the conjectures, very important conjectures of Claude Berge. And actually the solution of the strongest conjecture of Claude Berge was a paper more or less 200 pages long, published in Annals of Mathematics. So it doesn't happen every day that Annals of Mathematics publishes a paper in combinatorics, and 200 pages long at that. Okay? So you can see here Claude Berge, already as a mature man, and next to one of his passions, which is statues. And here he is next to a statue by the favorite sculptor of my wife. So I won't tell who he is. Okay. So now here is graph capacity. I guess you all know this. And in the very special case that was that made it famous outside the information theory community, the pentagon graph. So in the pentagon graph, you just have, 5 symbols circularly arranged, and every vertex is connected by an edge to its neighbor on the circle. And so now this is actually an interpretation that is complementary to the original one by Shannon, the way he used the complementary graph to represent this, but I have several reasons to prefer this representation. So if adjacency of edges is interpreted as distinguishability in some particular concept, so you look at your symbols through a noisy channel, so to speak, and which are the pairs that you can tell apart. So this is represented by the graph. Now, so if that is your interpretation, then it comes naturally to extend this relationship to strings of your symbols, in the following way, that you would say that two strings are distinguishable if going through the pair of the strings, coordinate by coordinate, you find one coordinate, say I, where you can say, aha, here they have two distinguishable symbols, and therefore the two strings are distinguishable, period. So, this, what it defines is a concept of power of graphs. Well, actually, it's a product of graphs, but I won't go into this. So in a purely graph-theoretic language, then the graph capacity of Shannon's is to determine the maximum, well, the non-asymptotic step is to fix a block length, and then consider the maximum cardinality of a set of pairwise distinguishable strings, okay, of that length. So that is called, in the graph theory language, the clique number of this graph, of this power graph. And then you evaluate this asymptotically, so you consider the nth root, just to renormalize, and then since we are in information theory, you also take the logarithm to express this in bits, and this is the capacity. And the limit exists by a lemma of the famous tutor of John von Neumann in mathematics when he was a kid, one Mihály Fekete. I mean, this is very elementary. But it exists. Now, so when I was a first-year student, it was already a very famous open problem to every combinatorialist. And actually, Tibor Gallai, the great Budapest combinatorialist, taught us about this when we were first-year students. So what is the value, what is the capacity of the pentagon? It looks so easy. And so Laszlo Lovász, who is a specialist in solving problems 25 years from their introduction, showed no, really, I don't mean at least 20 years. It's more or less exactly 25 years. So I don't know how he does this. And so he showed, so there was this lower bound and the upper bound that Shannon knew and everybody knew. I mean, nobody improved on Shannon's bounds before Lovász came, and they both looked more or less the same, so it was hard to decide which one would be the truth. And actually, Lovász showed that the upper bound was the truth, and for some reasons I won't go into, this is still a very special case. So for C7 and its complement, the problem is still wide open. Okay, so we should wait at least another 25 years, so maybe this year, maybe just this year, Lovász will solve C7. Okay. So now we introduce the hypergraph capacity, like I said, and you can easily guess, even if you don't read it. And so the difference is just, like I said, the simplest case of this hypergraph capacity problem that refers to a true hypergraph. And what I most like about this is that actually these different generalizations that I would like to talk about of graph capacity bring, at least as far as I'm concerned, an unexpected homogeneity into extremal set theory. So it goes in the direction of moving extremal set theory and extremal combinatorics from an anthology of anecdotes to something like a theory. And that's because you can use information theory that is a theory. So maybe the problems are not anecdotes, they are very long to state, but then they stick together. Okay. So we actually introduced Sperner's capacity and called it such because this is a generalization, a formal generalization of the favorite introductory problem of Paul Erdős to what he called extremal set theory. This is a problem stated and solved by Emanuel Sperner in 1928, and so now it's common to call a family of subsets of an n set a Sperner family if no two of them contain each other. And so the question is, what is the largest cardinality of such a family? And the answer is that this is the middle binomial coefficient. And actually, in some sense that I won't explain here, it would be easy, but I don't have time. This solution is unique. But what I would like to show is the special case of a new capacity problem that we came to call Sperner capacity. Well, in the case that is concerned with Sperner's problem, actually the Sperner capacity is trivial, and Sperner's theorem says much more. Because what we would be looking after is just the exponential growth of the largest Sperner family. And that is perfectly trivial without Sperner's theorem. But it's conceptually a special case of the Sperner capacity, which was also the reason why we called it Sperner capacity. And we were very close with Gabor to introducing this, but for biographical reasons we have failed. And so in this paper with Luisa Gargano and Vaccaro, we introduced it formally. So, this is just a formal generalization. If you use the complementary language, the one I used, then this is really a trivial generalization in that language of Shannon's graph capacity. So you just consider directed graphs, and now distinguishability is an asymmetric notion. So being able to distinguish a vertex from another doesn't mean that you can do it also vice versa. And so you have a directed graph, which means that the edges are just ordered pairs of vertices. And now, instead of a clique, you consider a symmetric clique. So a symmetric clique is a maximally connected subgraph. That is, every vertices, so you have a subgraph that's induced by a subset, but every two vertices of this subgraph are connected both ways. Okay, so so in that sense, it's a natural generalization because clique is maximally connected in an undirected graph, and here we have a directed graph. And then you define, the prior graph in the very same way as before. So x can be distinguished from y if at least in one coordinate, but this is now asymmetrical. This is done. And then you evaluate the largest cardinality of a symmetric clique in this prior graph, and then you normalize it the usual way, and you go to the limit, and the limit always exists for the same reason as before. So why is Sperner a special case of this? Well, if you have an n set, then you can characterize the subsets of the n set by their characteristic vectors. And these are just binary strings of length n. Okay? And the relation that these sets in the Sperner family should not contain one another means that for any two of your strings, you should have the only edge both ways. So you should have somewhere a 0 in x and a 1 in y, but you should also have this vice versa. And we started to, consider such problems with Gabor-Shimony. And then we made another important generalization, important for our capability to solving problems of Shannon's graph capacity, which is the capacity for a family of graphs. And I'm really running out of time, so I won't even use the definition. But once again, so you have a family of graphs, and now you are looking for the largest subset induced in the nth power of the vertex set. So induced in each of your graphs of the family. Okay? And so then you ask how large this can be. Okay. And so this we call the Sperner capacity of the graph family. And so now you have, the graphs are directed. That's one aspect of the generalization. But they are also you also have a family of graphs. And that's another aspect of the generalization. And I will just run 2 minutes over time if my president allows me to do so. And so, what is nice is that we were able to come up with a max-min formula for the capacity of a family of directed graphs. Now, this formula is a max-min formula that is in terms of quantities that are, just to give you an idea by the name, are capacity of the individual graphs in a fixed type. So instead of considering arbitrary sequences, we consider sequences of a given type. So here is this parameter that is can be characterized by a distribution. But if the graphs are, and we know that not even the capacity of a general graph can be determined. But in the case these graphs are nice, so the graphs in the family are nice, then we can do this explicitly, and then our max-min formula becomes explicit. So if, for instance, all the graphs in the family have a single edge, then here you have this explicit formula for the Spanner capacity that you have in blue. And now it turns out that the problem of Rény's about qualitatively independent graph families can be phrased in this language. It's the problem where the family of graphs are all the edges of the complete graph. Okay? And so therefore our formula becomes extremely simple and just gives the solution of Rény's problem. And so the construction part is the important part of what we did. And we saw that this has nothing to do with classical information theory, because a directed graph has no meaning, we saw in information theory. But if you have a taste for information theory, and if you are using the information theoretic intuition, then this drives you even to places you would never want to go to. And you won't even get a ticket. By the way, maybe I got the ticket, but I was not doing the driving on that day. So, okay. Anyway, yeah. So anyways, Nyack and Rose were the ones who understood. So actually what we did gave a formula for the compound channel problem with an informed decoder but an uninformed encoder. And then Nyack and we didn't need directed graphs for that, just the capacity of a graph family. But then later Nyack and Rose noticed and proved that if you want even the decoder to be uninformed, then you can still find the capacity of the compound channel by using the general framework of the capacity of a family of directed graphs. So it's not true that this was irrelevant to the problem. So just as a last sentence, because I really ran out of time, so you see, here are the things that I can talk about. I would like to tell you that then we generalized capacity, and we introduced capacity problems for permutations. And let me just finish with one of those puzzles that you get by doing this generalization. So it's a puzzle, but it's an unsolved problem. So maybe you would like to look into it. So we said, so consider a set of permutations of the first natural numbers. Permutations, that is. And I would say that two permutations are colliding if, like cars, so if they touch, in the sense that there is at least one number between 1 and n that they map into two neighboring numbers. So this is a condition that means that, in order to fulfill this condition, those permutations have to be different. So how many permutations you can have maximally? So what is the largest coordinate of a set of permutations that are pairwise colliding? Okay? Now, I don't know the answer. We have lower bounds and upper bounds, and we conjecture that this maximum number, for completely different reasons from the Spanner problem, but this maximum number is still the middle binomial coefficient, which would put the rate at 1. But if this nice-looking conjecture is not true, then this maximum rate is an interesting quantity. And also, so this is a different generalization of capacity, because now you have an infinite alphabet with your permutations. And now we believe that maybe this is not a problem in classical Shannon theory, but actually it's a generalization of graph capacity in the Shannon sense. So, you know, this is what drives me, not away from information theory, but maybe it drives me circling around and around at the outskirts of information theory. Okay, so thank you for your attention.